So welcome back, everyone. Now we have the pleasure of having Paolo Carpeggiani from Vienna. He's going to talk about high harmonic generation, the route towards bright sources in the soft X-ray spectral range. Thank you.
Thank you. So I start by thanking the organizer again, not only for inviting, but also for making all these nice social activities and making such a pleasant environment for this conference. So thank you. I will start with a quick introduction on high harmonic generation. I have to assume that most of you are not from the field. I didn't see many people in the seminar too, so I guess you are more from other fields of research. And then I will show some works from our group for the improvement of high harmonic sources, in particular with the development of the driver, so basically the laser sources. Okay, so some introduction for those of you who don't know. The others will excuse me for the bit of long introduction. What is high harmonic generation? So it's a process of frequency up conversion from the near infrared laser driver and into the XUV or soft X-rays, depending on several parameters. It's an extremely nonlinear and non-perturbative process. So what happens exactly? If we look here, when we focus a femtosecond linearly polarized near infrared laser into a gas jet at high intensity, so about, we see 10 to the 13, 10 to the 15 watt per square centimeter, the extremely nonlinear interaction of the laser with the gas results in the generation of XV pulses. If we take a look at the properties of the generated spectrum, we see that we have a comb of odd harmonics of the fundamental, that is the frequency of the laser driver, and we see three regions in the spectrum, a perturbative one where each consecutive harmonic quickly drops in intensity, a long plateau or the sign of a non-perturbative process where all the harmonics have more or less the same amplitude, and then a region where there is a sharp drop in the intensity of the harmonics, which is called the cutoff region. Very interesting, if we want to do very ultra short pulses, the fact that we have XUV radiation with very broad bandwidth would support, if we have coherent radiation and if we have the proper spectral phase, would allow us to have attosecond pulse train with a certain spacing and a certain duration. So a typical question, can we also get isolated attosecond pulses? Yes, that's not the purpose of what I want to mention here today, but indeed, if we use shorter pulses or if we confine the generation of the harmonics to a very short time period, we can generate a coherent continuum in the XV spectrum, and this would support a single isolated attosecond pulse. More in detail, we can see that for each half cycle of the driver, a continuum spectrum is generated, and the harmonic structure actually results from the interference of this process being repeated every half cycle of the driver. Okay. Other typical question, I mean, why attosecond pulses? Well, the typical image that we have is that by improving the temporal resolution of our camera, we can improve, of course, the resolution of our time resolved measurement. So basically, we are building a tool which is able to monitor ultra-fast dynamic in the nano world. Just to be clear, I mean, in the quantum world, the light pulses are both the bullet and the camera for these experiments. So basically, we have to keep in mind that we need two pulses to retrieve time-resolved information. That's a common question that I get. So what are the ultrafast dynamics? Well, are those that occur in quantum system with extremely localized in space, so with high energy and very short typical time scales. As we see here, the more we go to shorter space scales, the more we go towards higher energies and consequently to faster time scales as well. Also, you have seen in the presentation also by Tenio yesterday, there was the award of the Nobel Prize in Physics for the attosecond science last year, and specifically for the first observation of high harmonic generations and for the development of those techniques which actually allow to see the attosecond temporal profile for the attosecond pulse train and for the single isolated pulses. So these are XUV near IR techniques which actually provide the temporal resolutions which is needed for investigating ultrafast dynamics. And something very important, so we see the first observation was in 1987, and the first time resolved measurement showing the temporal structure of these harmonics in 2001. And in between, in 1993, there is the semi-classical three-step model, which actually explains all the observed behavior in all the spectral features that we just saw before, and also predicts the temporal behavior, which was actually shown a few years later. So in the semi-classical three-step model that we have seen already, but let's see once more. So basically we have our atom in its ground state, and when we focus the laser due to the strong field of our focused near-infrared femtosecond laser, we can distort the atomic potential to the point where an electron may escape through tunnel ionization. And then, upon releasing the continuum, can be accelerated away from its own parent ion, and upon reversal of the electric field of the laser, accelerated back with high energy, eventually to recollide, and eventually, with very small probability, to emit a single high-energy XUV photon. The nice thing of this model is that it allows us to calculate the energy of the recombining trajectories of this electron in a semi-classical way. So what are we looking here? In the dashed line is a period of our near-IR laser driver, and the color lines are the electron recombining trajectories, and the color scale shows their energy. So what do we want to learn from this? Well, a lot of interesting behaviors, like the relation between the ionization, recombination time, and the electron energy, and therefore the XUV energy. The fact that we have long and short trajectories, that we have a subcycle process, extremely coherent and also very delicate. But I want to bring your attention to the fact that basically we can derive an expression for the cutoff energy, which is a function of the ponderomotive potential, so depends on the intensity and on the square of the lambda, being the wavelength of our near-IR driver. Also, with some additional models, we will see that the XUV flux drops with the dependence which is opposite in lambda. So one already starts to get the point that by changing lambda, either loses cutoff, maximum, that is the maximum photon energy that can get, or it loses a flux over all the spectrum. So we start to see that we have some annoying trade-off in this process. On top of that, this is the single atom response. If we want to have an observable macroscopic effect, as in all the frequency conversion process, we need to consider the phase matching conditions. So basically that the near-IR driver and the generated harmonics are in phase over the volume of the interaction medium. We are probably confident of the phase matching conditions, for instance, in nonlinear crystals, how to achieve phase matching conditions in this situation. Well, actually, we have a series of terms, some of which they have opposite sign. In particular, let's focus on the neutral gas dispersion and on the plasma dispersion, which means that as they have opposite sign, it means that by balancing very carefully the intensity of the laser and therefore the ionization rate and the pressure of the gas, it is actually possible to minimize the phase mismatch between the driver and the generated harmonics. On top of that, once you reach the phase matching, you have to take care also that the gas from which we are generating the harmonics is also absorbing them. So that's another factor to take care of. The summary of this slide here is that we are considering a very delicate process. We need very fine tuning in the laser intensity, in the gas pressure, and in the geometry, the way we focus the laser, the relative position with respect to the gas cell, and so on. Or basically, if we want to increase the flux, it's not that we can just say, okay, we have the harmonics from the nonlinear interaction of the laser with the gas, let's just increase the laser intensity, or let's just increase the gas pressure to maximize the flux. This doesn't work at all, unfortunately. However, one can keep in mind that one can increase the repetition rate of the laser. It doesn't appear anywhere in the equations that we saw so far. Or one can increase the energy, of course, at the condition of preserving the intensity of the laser in the focus. That is, by using longer focal lengths, you can increase the energy while preserving the optimal intensity. So how a typical HIG experiment look like? On the left, we see an ex situ experiment, so basically the one in which we do pump probe to retrieve information on ultra-fast molecular dynamics, for example, and in which the HIG process is used as a attosecond XUV light source. So basically we have a source here, and we have a scheme to introduce a controllable delay between the XUV and the near IR, and then we shoot on a second gas jet, or on a liquid, or on a solid, basically on our sample, and together with some diagnostic, we can do our experiment. And the thing here is that this type of experiment has extremely high requirements. So we are operating at the very limits of the available laser technology. And there is another class of experiments called in situ, in which we have only one gas jet. We don't have a sample, usually. And they're used for the investigation of basically, or for the optimization of the light source. So we may want to see how the harmonic generation behaves as a function of the laser pulse parameters, for example, the wavelength, or with some complex shaping of the electric field of the driver, like polarization shaping, multicolor, and so on. And we can do also a few other experiments, like HIG spectroscopy, for example, in molecules or in solid. You generate harmonics, and looking at the spectrum as a function of the laser parameters, you retrieve some information on the behavior of the system. In this case, is a gas jet, but more recently also solids have been very popular for this scheme. So the experiments that I'm going to show are of this type. So for the optimization of the light source to be used in this type of experiments. Another thing, not only in this experiment we operate at the limit of the laser technology, but also we may need a series of further processes. So let me go back 1 second. So what's on the left of these images here, so what we have before the HIG setup, where this light comes from. Well, it may come up from a CPA laser system, but we may also need a series of intermediate transformations. For example, we may need to do pulse post-compression. So we may want, if we consider, for example, that we have a very typical titanium sapphire laser as source, and let's say that it delivers 2 millijoules 30 femtosecond pulses, we may want to apply post-compression to have, for example, 5 femtosecond pulses, but then we'll have roughly half the energy. Or we may want to do some frequency doubling, we will have a bit less than half the energy, or some tunable frequency shift towards longer wavelengths, and this will give us with much less than half the energy. So the problem of the source for this type of application is quite stringent, and that's what we will be seeing next. Of course, you might be wondering, okay, very nice, but are these high harmonics useful for something? Well, yes, for quite a lot of stuff. So let's consider that not only we have attosecond light pulses, but also that the electron, we have attosecond electron wave packets generating the XUV, and that can be generated by the XUV. And they can be used, for example, as for ultra-fast sampling or to build basically a petahertz oscilloscope. Plus, we have XUV light pulses. I mean, this gives us direct access, for instance, to inner shell electrons. So this also allows us to measure electron dynamics with few attosecond resolution and to answer questions like how long does photoionization takes, and how much is it affected by resonances or by the environment, or how fast is Auger decay. It's possible to initiate ultra-fast dynamics in molecules and to monitor them. And it's possible to develop techniques for time-resolved, element selective, and chemically or magnetically sensitive measurements. Okay, so this was a quite long but necessary introduction to the topic. What I need you to remember. Okay, the XUV pulses so are quite great and useful. However, they're limited in spectrum, in flux. They're driven at the limits of laser technology. We may need extra techniques that cost extra precious energy. We have the full understanding at the microscopic and macroscopic level. This we can take at our advantage. And let's remember, we cannot just increase the flux with the simple tricks. We have seen also other information which are nice, but they're not strictly necessary for what I want to present you now in this talk. So what I'm going to show. So basically some optimization. So we have seen that there is the limiting spectrum, so we will want to see the limits of the cutoff by using mid-IR sources, so by increasing the lambda. So how much can we push that? Or we will see also how to optimize the laser technology in order to optimize the XUV flux in specific targeted spectral ranges. But I will start with some experiments from our group about trying to overcome the limits by controlling the trajectories of the electron as we saw them in the three-step model. Another little introduction is the last one. I will mention the OPA quite a few number of times. So what are OPAs, optical parametric amplifier? Well, that's a bit complicated. Let's see simply what they do. They convert a portion of the energy of our pump, usually the output of our laser system, into two longer wavelengths or two smaller frequencies with a certain efficiency and with a certain tunability range. So as you see, we have our omega-3, which is the pump, from which we obtain omega-1 and omega-2, which are smaller or two longer wavelengths. And we can start to see that, for example, if our omega pump is the output of a titanium sapphire laser, we cannot generate any arbitrary wavelength. We have a range of possible generation. And the same for other type of lasers. So in general, we have an optimum at half the frequency or twice the wavelength. Okay, so in 2009, there was this theoretical paper from Imperial College in which they asked themselves, okay, the limits on HEG given by the fact that we're using a sinusoidal wave. But what if we use an arbitrary shape of the wave? I mean, there are simulations, we have the degree of freedom to use any shape that we like. And they figure out that by using a triangular ramp, they can have quite much of optimization on the harmonic signal. Okay, this is not really a real case scenario that you can actually generate a shape like this one. So they consider also the options to make the superposition of a few sinusoidal shapes at different wavelengths. So what they did in our group was, okay, they say, let's give it a try. My group is specialist in laser sources, laser development, and OPA. So they well thought about trying to make a combination of different frequencies and to see if it is possible to generate this perfect wave and which kind of improvement you can get. As we see, they use, in this case, an ytterbium laser. And here we see the part of the energy from the laser is split to go to an OPA to generate the longer wavelength. And a part is also converted into the second harmonic. So there will be a frequency at 515, 1030, and 1500. So omega, 2 omega, 3 omega. Okay, they gave me this nice movie for that. Okay, what is the movie showing? Here on the right we see a clock with two hands. There is one which is moving quickly, which is basically the CAP, or the phase offset, which is a parameter which is normally not controlled in our laser systems, unless we put an effort to stabilize it. And the green hand is the phase that we put between the different frequencies, and is something that we control, for example, by tilting a plate with a specific dispersion. So what this movie wants to show is that if you use commensurate wavelength, like omega plus 2 omega, use commensurate wavelengths. Okay. So basically, whatever value you have for the orange hand, the shape of the field stays the same, and it's only affected by the part that you control, by the green part. If instead you use two non-commensurate wavelengths, like omega and 1.5 omega, as it is the case between the 1000 and the 1500 nanometer in this experiment, it's basically important to fix this parameter, which is something that they had to do for this experiment. If we go to see what happens when we have only, for example, the 1030 nanometer versus at least two wavelengths combined, we see that there is quite an increase in the flux of harmonics. And another interesting aspect, so we were saying that the spectral features of the harmonic spectrum depends on the interference, on how often we sum the spectra in the Prism model. We see that here the periodicity of the red wave is 6 times the one of the blue wave. So in the blue wave we have the generation every half a cycle, and here with the red one we have a periodicity which is 6 times more. As a consequence, the density of harmonics in this case is 6 times more, and the spacing in time also will be accordingly larger. So the results, so basically they compare what would be the yield with each of the colors individually, and to show that when they're all together, you can indeed extend the cutoff and much higher flux. So basically, it's a way to say that they demonstrated successfully the trajectory control by the use of multicolor fields. Another work which was done by our group in collaboration with Gila, and that for those of you who saw the presentation by Tenio yesterday that mentioned, is the generation of kilo electron volt harmonics by using long wavelength mid-IR drivers. So basically, the idea is the following. We know from the theory that we have a single atom cutoff, which scales as lambda square. They made the calculation to see that considering also the phase matching conditions, we have a similar dependence, anyway, a bit less, but okay. But the question is this actually true? I mean, if we go to a much longer wavelength of the driver, will we actually get a much higher photon energy for the XUV. Yeah, that's quite a counterintuitive in general. The lower the photon energy of the driver, the higher the photon energy that you can get. Well, the trick is that you get less of it. Well, then they also made some simulations to verify which kind of gas would be best, because if we look at the previous slide, one can see that there would be the option to choose like a shorter wavelength with helium or a longer one with neon. So the question would be which would be the optimal configuration. So they concluded that it was best to use helium. And indeed, by applying a 3.9 micron driver in helium gas cell, they managed to demonstrate this record value of 1.6 kilo electron volt of coherent harmonics. That was a result which is still impressive nowadays. Just to get an idea, also it's important because when we extend the spectral range of the harmonics, we go to cover a series of spectral regions like magnetic edges, the water window, including the carbon K edge absorption spectrum, and going even to higher energies, we go to cover the magnetic L edges. So it's possible to make investigations on this type of materials with elemental sensitivity. To get an idea of the improvement, we see what was the progress back at the time. So this was a huge jump, which inspired the confidence, let's say, to proceed in the pursuit of high cutoff harmonics by using mid-IR drivers. Not to this level, we will see, but also in this direction. A few words about the driver, which was the part which was provided by my group. So OPA are quite complicated. I don't have the time or the intention to kill the audience with the details about that. But okay, we can just see the parameters. So basically, we have our 3.9 micron at 25 millijoule. That's quite a unique system. Operating, you see a quite low repetition rate, 20 Hz. And just to get an idea of what kind of setup is it, well, we see a picture of the people operating it. It's here. And there are a series of slides in which I will just pass through quickly to see how complicated is this setup. So we see a few blocks, but each of them is quite a complicated system. We don't have the time or the purpose to go through it all here. Okay. So as a last part, I would like to show you this work in which I personally led, actually, unlike the others, which is the harmonic generation at the carbon K edge, directly driven by SRS redshifted pulses from an ytterbium amplifier. We will see what this title means. But basically, the paper answered the question on how to optimize these sources in this interesting spectral range. Here we have the scheme that our student made, like if it was a kick-out phase of a tournament, that for the final you get titanium sapphire versus ytterbium and SRS versus OPA. I will discuss all these elements now. So why HAG at the carbon edge? I mean, obviously because you can do some wonderful stuff there. I mean, there have been some experiments published in 2017 by different groups in which basically they show that they can monitor molecular dynamics with unprecedented resolution, and basically because you operate at the transition from the carbon K edge, you have the elemental specificity because other elements would have a very separate line, but also you have the chemical sensitivity. So basically that's what you see here. The molecule has been exploded by a pump pulse and probed by XUV pulse. Well, in this case it's more soft X-ray. And you see that the molecular dynamics are tracked by the fact that the absorption line is changing according to the shape of the molecular orbitals. And we do not see only the initial and final states, but also we also see the transient states. And the same even for more complicated molecules from this other work. This also led to further investigation, even in the liquid samples, so basically to investigate molecules in their natural environment. Okay, it's quite an interesting thing. So let's go back to what I showed in the introduction. So how are harmonic done? We focus our laser in the jet. We cannot increase the intensity. We cannot increase the pressure. We can operate at an optimal driver wavelength. So we will have to see what we mean by optimal. And then we can do the power scaling of our laser source. So what is an optimal driver wavelength? Considering that we have two laws with opposite dependence, so we have one factor which goes up with lambda and the other which goes down, it means that there is an optimal lambda. And I like very much this paper here because it shows it quite well. So if we go at shorter wavelength, we have very high flux, but we don't reach certain spectral regions. If we go to much longer wavelength, we cover a broader spectral region, but we have much less flux in the intermediate one here. So if we want to have high flux of harmonics in this spectral region here, obviously we will want to go for the red curve. So we don't want to overshoot our driving too much. And that's basically what we see from this plot. Here we see the driver wavelength, and here we see the achieved HLG cutoff from the results from the literature. And basically we could say that these points here corresponds to this line, and these points here correspond to the blue line. Also in this case, one has to wonder which would be the best combination of wavelength and gas to be used. That's quite complicated. I mean, the physics tells us that would be helium, but one also has to consider that not all the laser wavelengths are available with the same parameters. So one has to think about which wavelength is available with which parameters and with how much energy. So if we go to take a look at the literature and the results, basically what one sees, so most of these are experiments which also showed PAM probe, so real spectroscopic investigations. So the first thing that one noticed from this table is that most of the works have been done with the titanium sapphire, which is the classic laser for HAG experiments, in combination with an OPA or with an OPCPA. And that there are just two which are with ytterbium plus OPA. And we see for the choice of the gas, indeed, it's mostly helium and neon, going from 300 until 500 electron volt cutoff. So once again, let's see the image of the OPA. So with the titanium sapphire plus OPA, we can reach this optimal wavelength here, quite at the edge of the efficiency of the OPA. How about if we use ytterbium lasers at 1030 nanometer? In this case, the optimal range that we want to get is out of the tunability range of the OPA. So it's not a good option. So far, regarding this work, we have seen that with the harmonics at the carbon edge, we can use, for instance, to monitor the molecular dynamics of all the molecules which are carbon-based. Of course, I don't need to remark the importance of that. But we would like to have more flux for them. And also, we have seen that, unfortunately, the HAG driver for this type of experiments is not directly available from a laser amplifier. So an intermediate conversion step is somehow necessary. And these, once again, they cost efficiency. So this is the scheme that we want to optimize. We have a laser source. we have some process like frequency conversion or post-compression to make the pulse shorter, which allows us to form our HEG driver. And then we have our process of HEG in gas. And so basically we want to have a system which allows to optimize all of the 3 steps. It's quite pointless to make an optimization of a factor of 3 in one step if in the other step you lose the efficiency by a factor of 5. So if we want to use ytterbium lasers and we want to access this region here, the question is, instead of going with OPA, is there a way to get a small frequency shift? Well, if I make this question, it's because the answer is yes, as usual. Probably it would be enough to use some inelastic scattering, like Raman scattering, that very surprisingly was not demonstrated for high energy femtosecond pulses till just a few years ago, in which there were 3 papers by 3 groups, including ours. Basically, well, how it works is a bit complicated, but let's see what it does. Basically, it produces an asymmetric spectral broadening, or in other terms, we have a spectral broadening plus redshift. Or, another way to put it, we have the frequency shift and the pulse compression in a single efficient step. So we start to have all our ingredients. The question if it works. After overcoming few of technological problems that most of the available optics are calibrated for symmetric spectral broadening, so you don't have the bandwidth to go to the redshift as much as you need, so you need some new piece of optics. But once you do that, indeed, you manage to reach the target region. Actually, here we show the difference in harmonic generation in red and blue when you drive with symmetric and asymmetric redshifted spectral broadening. So one can see the advantage there. Okay, the point is, okay, we reached there, many people did before. What's the point of this? The point of this is that it can be done with a higher efficiency and more power. If one is quite expert, can go through this diagram, but let's put it this way. Titanium sapphire is a well-established technology which kind of reach its intrinsic limits. Intrinsic limits like the quantum defect in the pumping. While ytterbium laser are a quite young technology which has a lot of potential for further power scaling. On top of that, OPA are limited in efficiency, while the SRS we can have values around 60, 80, so it's very promising. Okay, this was one of the first demonstrations of getting to these regions without the use of OPAs, and but the important thing is that it's a new scheme which is suitable for power scaling. Now, let's see just a few parameters. So this was the table of the literature, very big one. I mean, let's focus on some part. Now I highlighted some stuff. So like which schemes offer some record values and some trade-off are necessary. But I would just like to bring your attention to the fact that even though we use the quite modest laser system, we manage already to have the most powerful driver for this type of application. And we actually used a 6 watt laser. Well, we had the 7 watt, we used the 6. But for instance, our group now is working on developing a 100 watt laser system. So one can understand that with this value we'll get a source which is way more powerful than most of the ones that we've seen in the literature so far. So with this, it's time to conclude. So I've shown some of the experiments done by our group in the attempt to improve the flux or the cutoff of the HEG sources. We have seen in one how to overcome the trade-off between flux and cutoff by manipulating the quantum trajectories of the electrons. We have seen this very important demonstration of phase-matched harmonics in the kiloelectron range with a mid-IR driver, so with this record value of 1.6 kiloelectron volt. And we have seen the problem of optimizing the laser source for applications, for instance, until the carbon edge, let's say in the range 100 to 300 electron volt. And with this, I would like to thank you for your attention, and I'm ready for questions.
Thank you, Paulo, for the very nice talk. Questions?
Yeah, thank you for a very nice talk. My question is about, let's say, increasing this power. So what is the next target for this, let's say, the power that you need to enable some new application or so? Is it just the more power you have, the better, and that's what you're going for? Or is there like, okay, if we have this much flux, we can do these experiments that have never been done before?
So these kind of experiments, like the ones in the carbon edge, are a very big pain to do, and few groups in the world can afford, with the current schemes, the hardware to get it, which is basically the biggest ISAF laser that you can imagine and most expensive, with an OPA which supports the power of it and deliver the pulses that you need for it. So on one side, there is the fact of making a scheme which can deliver more power with a simpler scheme. So terbium lasers are way simpler and cheaper than titanium sapphire. They don't have the same performances in terms of pulse duration, but this can be compensated by post-compression. So on one side, you can have a simpler system, more economic, and eventually you can get more power. Now, what are you going to do with more power? First of all, you get hopefully a decent amount of flux. So basically you can operate a bit more above the noise level, because this is what we are talking about. And second of all, you have to consider that if you start to do experiments in which, for example, some molecular dynamics, some chemical dissociations as possible different outcomes, and they have different branching ratios. So if you don't have much flux, maybe you will be looking at the reaction which covers 90% of the probability. But if you want to start to take a look at something which maybe has 10 or 5 and later 1% probability, you need to have a source with enough flux and of course stability in order to do that. So basically these are wonderful experiments, but very few labs are able to do it. Hopefully in the future will be more.
Okay, thank you.
More questions? So I see that with these techniques, you are already saying something about chemical reactions. How far-fetched would be to see things in living tissues for the biophysicists in the audience?
Well, I think you should, okay, with the XUV. Well, actually, regarding living tissue, maybe you should ask Ferenckraus. That is quite interesting. Well, it's not in living tissue, it's in blood sample. But I would say that we are still far. However, as I mentioned, there have been demonstration of probing molecular reactions in water jets. Now we are still talking about water jets into vacuum chambers. And these XUV radiation, even though like when we go to the beach, we put the sunscreen to protect ourselves from UV, is because they come from the sun. While here the amount of light that we have wouldn't survive a few centimeters of propagation in the air. So basically we are still limited in operating in vacuum setups. And maybe, however, with the near IR techniques, it will be possible instead to operate, of course, for different purposes.
More questions? If not, let's thank Paul again. So now we have Gustavo Wiederhecker from Campinas. He's going to talk about embracing the potential of nonlinear integrated photonics beyond silicon, advantages and limitations. Thank you, Gustavo.
Okay, thanks for having me here. It's really an honor to be in this plenary session here. And the conference keeps packed despite the long days till we get here, right? So I'm coming from the University of Campinas. For those who are not from here, it's about 120, 130 kilometers from São Carlos, towards São Paulo. And today I'll be talking about to you silicon photonics and things that derive from it. And I chose these two Blender pictures that illustrate two devices that I'll be discussing today and probably will give you a perspective of what kind of things you can do in this platform. So this whole field derived from the need for higher bandwidth communication. So it's worth reviewing a few points. One is, you might not be aware, but there's nowadays over 5 billion kilometers of optical fiber deployed over the world. This is the distance from Earth to Pluto. And only Corning, one company, has sold over 1 billion kilometers of optical fibers. Of course, that keeps a very large production of fibers. About 400 million kilometers of fiber are produced every year. And there's only one thing that beats that, which is Italian pasta. So I made this calculation. The Italians in the audience might correct me, but apparently Italians consume about 23 kilograms of pasta every year. So the approximation I made to get this number is that I'm assuming it's all this pasta is coming into spaghetti number 5, which is 1.1 millimeters in diameter. So just to give a perspective, only food beat fiber production in nowadays. So of course, this is not only for long-range communication, but also in data centers that are coming more and more frequently nowadays. There's a large demand for optical fibers. This is just a picture of a data center where you can see the computation nodes, and they're all connected by fiber interconnects. And the infrastructure is more or less like this. You have this electrical cables that handles up to 10 gigabits per second, roughly, connection. And then you pile up all these electrical cables and you send down to fibers. Then you can reach all the way from 3 to 10, 12 terabit per second data rates being transported within these data centers. And Cisco, the company, puts out a yearly report on how eager we are on this business. And the growth has been tremendous over the last decade. So we went all the way from 6.8 zettabytes, it's like 10 to the 12 gigabytes, 1 zettabyte, all the way to 20 zettabytes in 5 years, from 2016 to 2021. And what is a bit depressing, though, is that if you look at what happens actually, is most of this data is being used for social networking and video streaming, right? So maybe TikTok and Instagram and all those things are driving the whole thing. And of course, video streaming, when you talk about what goes out of the data center to the user, is by large the highest demand here. Anyway, to keep up with that, this is not the end of the game. So right now, about 63% of the world population has access to internet. So there's a way to go till we connected the humans. But there's also a large number of new devices being connected to the network, which is this IoT, Internet of Things idea, right? And there's roughly expected 75% of the connected devices across the world will be by IoT applications. Bandwidth about 110 megabits per second, so we need to improve that and push further the communication infrastructure. So of course, if you want to deal with that, you need to choose a platform that's mature, that allows you to do mass scale production of all this. And of course, silicon is the name of the game. So nowadays, if you look at the astronomical scale that silicon is being produced, we have enabled the production of over 10 to the 18 transistors every year, and that boils down to reducing the cost of transistors. And you can count the cost of each transistor in your CPU through nanodollars as a standard unit. It's about $1 nanodollar per transistor. And this has been this has been sort of predicted by Rick Seraph back in the 80s. And he put out this review paper in the early 90s where he discusses that, maybe the 1990s will be the decade for building these silicon superchips that merge silicon photonics with advanced silicon electronics on a single silicon substrate. And he ends up concluding that also hybrid integration techniques and monolithic might play a role in this game. And Rick was off maybe by the time it took to reach this regime. But if you look nowadays, by 2012, IBM announced this foundry scale production of silicon waveguides overlaid on electronic circuit that enables the whole field of silicon photonics for companies and for customers and scientists. It turns out, though, that silicon is a pretty bad material, if you think about it. It doesn't have a direct band gap, so no light coming out of it easily. There's no Chi2 because it's cubic crystal. And on top of that, even though you're operating below the band gap, you have quite large nonlinear photon absorption. So you can't really drive it too strongly. Despite that, the community over the last 20 years, let's say, have been really creative in finding solutions to extract functionalities out of this pretty poor optical material. And for example, this is a seminal work by Michal Lipson's group where they demonstrated a modulator based on carrier injection in a silicon waveguide. This is work by the Gantt group, this is Roe Bates here, showing that nowadays you can actually grow defect-free 3.5 semiconductor on top of silicon and bridge this lack of light generation ability of silicon. So this is what Seraph predicted back then as the hybrid integration approach. And nowadays there are 2D materials being poured in silicon, lithium niobate over silicon, there are all kinds of things. So again, even though people like to say silicon photonics, it has gone way beyond in terms of what kind of materials you can integrate in this platform. So of course we are confining light to really small spatial scales, so you can get a sense of this platform. On one side I have a silicon photonic typical waveguide. You have a core, a guiding core out of silicon, silicon nitride or some high index material. The refractive index contrast relative to the cladding around is rather high, 0.5 up to 2, depending on the material choices. And the diameters of these nanowires are usually below 1 micron. And on the fiber side, for reference, the refractive index contrast is about 5%, and the core diameter is rather large, like 8 to 10 microns, depending on the fiber type you purchase. So there are two different scales here, and when you talk about loss, which dictates how long you can propagate light in these structures, still fiber beats by orders of magnitude what you can do in silicon or silicon-based platforms. But if you put these two pictures in scale, that's about what you get. That's the size of an optical fiber mode relative to a silicon waveguide mode core. So there's roughly a 2 orders of magnitudes contrast between mode area in one platform compared to the other. So you can expect for nonlinear optics, this is great because you squeeze the electric field down to this really tiny place and therefore you get very high intensities and very large electric fields. So you can derive nonlinear optics effects from that. But that's not only the one thing that you get out of this, you also can, because of the high index contrast, you can tightly bend your structures. So this is a picture in our lab showing a silicon nitride waveguide going over a 50 micron band radius, guiding green light, and you can see that light pretty much bends very sharply without too much optical loss. And people have explored this, Tobias Kippenberg group in EPFL, show you that you can build these meter-long spiral waveguides inside the single photonic chip. The other thing you get is group velocity dispersion control. Right? So I'm putting this plot here, the frequency versus wave vector diagram, recalling that if you take the slope of these curves, you get the group velocity, right? So these yellow lines here are dispersion branches that you get by solving just a simple cylindrical waveguide. And I'm gonna iterate this graph as I change the core refractive index. So as you can see, what happens is that you get a much wider range of the denominator, the numerator here. The frequency is changing over a much larger scale. And therefore, you can expect that you can have much larger group velocity dispersion control using these techniques. And to wrap up, I think that's where it really stands out, is that this is a system-level platform. So you can not only build the waveguide, you can build waveguide, resonators, Mach-Zehnder interferometers, and you can add up in a single chip the whole set of devices that you may need to perform a given optical operation. So to give you in a sense, the typical standard silicon resonator can have a quality factor of about 1 million. So this means that if you put a 1 milliwatt, this amount of power that I get in this laser pointer, in a single resonator made out of silicon with a finesse that can reach up to the 10 to the 5, you can get circulating intensities of 80 megawatts per square centimeter. Okay, so this really alleviates the need for high power lasers to do nonlinear optics in this platform. Okay, so this is the sort of idea here. You can use this confinement of light to excite, read, control, manipulate, or your light-matter interaction using this platform. And it's no surprise that people have been really creative on this. So this is a few work, like for example, people doing like multi-dimensional entanglement on the system-level integration silicon chip. This is work by PsiQuantum in the Bay Area in San Francisco. This is Xanadu Corporation in Canada doing the squeezed state generation for boson sampling applications. This is work of Paulo Nussenswein at the University of São Paulo, also doing quantum light, quantum frequency conversion using this platform. And nowadays people are doing also entangled turnkey, entangled photon sources and whatnot. And I was happy to see a talk yesterday by Hiro Onodera that you can go even further and start like sort of doing dynamical printing of waveguides on this silicon-based, lithium niobate-based platforms that allows you to dynamically reconstruct these structures. Okay, so when you build these resonators out of silicon, the first thing comes in mind is probably Kerr optical frequency comb. So let me guide you through it. So we start with a CW laser, and instead of a pulse mode lock laser, you start with a CW laser. You shine this laser into a resonator. And in the resonator, you have the set of equidistance modes that are sort of controlled by two parameters. One is the group velocity dispersion that sets the free spectral range, how it varies with frequency. It can be anomalous or normal, depending on the geometry that you choose. And you also have the nonlinearities playing a role. So what happens is that when you increase your pump intensity, you induce through cross-phase modulation a shift of your optical resonances. So if you balance this cross-phase modulation effect with the group velocity dispersion, you can actually build a soliton out of these resonators. Okay? So I'm not going to go through the details of the mathematics here, but this is governed by what is called the Liggiato-Lefevre equation, and it has dispersion built into it, nonlinearities, loss, laser cavity detuning, and of course the laser drive. And what happens is that through modulation and stability of your pump wave, you start transferring energy to these other modes, and eventually if things get balanced enough, you can reach a soliton regime. So I'll just show you one animation that pictures the whole thing happening. So on one side, I'm going to show you dispersion. So this tells us that you have anomalous group velocity dispersion. Eventually you reach this zero crossing point here that might lead to dispersive wave emission. And I show here the electric field amplitude as a function of the round trip in a resonator. On the middle plot, I show a spectrogram of your optical intensity that will be varying as I tune the pump towards the resonance, right? And on the right side here is the intercavity energy variation as I detune the pump. And this lower plot is just a slice of the spectrogram, so you can clearly see what kind of spectral components are generated as I detune the pump. And this is going to give you a picture of what can happen in this sort of structure. So we start off resonance, energy slowly built in, you have a monochromatic laser in your resonator, but as soon as you reach this point, people call this Turing rolls, you have due to modulation stability, you create this four-wave mixing bands, and you form this sort of calm blinds inside your resonator. In the spatial domain, you see this sort of pulse being formed inside the cavity. If you keep pushing further, you go into this nonsense regime where chaos is prevalent, so things get very nonlinear, multimode interaction, you lose control of what's going on, but spectral domain gets very broad, even though there's no coherence between the spectral lines appearing here. But there's hope. If you keep detuning your laser towards the resonator, what you see is after you go through this chaotic regime, you start to see order coming out again, and this is what people call often the regime of soliton molecules, that you have a few pulses propagating inside your resonator, but you're already out of the chaotic region. But there's the sweet spot, even if you keep going further, which is if you stop your laser right at that notch that you saw in this intercavity energy, you can reach what's called the single soliton regime. So we have a mode lock laser source coming out of this initially CW pump laser in a compact platform. Well, this sounds like it's very special. You need to do a lot of engineering with this to get this working. But actually, if you look in the literature, all sorts of geometries have been explored to derive the soliton combs. And people, of course, when write papers say, look, I do engineering of this and that to get the soliton comb. But the truth is, what is common among these resonators that enables the soliton combs is that they're small, they have high Qs, and they have anomalous dispersion. And that's all you need. As soon as you put laser onto these devices, you get a frequency comb. That's the easiest thing to get in the lab rather than the more engineering perspective. Things may get chaotic once in a while, but overall it's simpler. So we did some of that. So just to give you one example, with a non-integrated resonator, just to take a microsphere, you can do that in your lab by just melting the tip of an optical fiber. And we did that, and we coated this very edge of the fiber with a very thin 100 nanometer thick aluminum oxide. And what this aluminum oxide does is it induces a level of control of group velocity dispersion. So instead of the mode shape, the optical mode shape, varying slowly as a function of frequency, by adding this thin layer of alumina, which has high refractive index relative to silica, you get this really abrupt change in the mode profile. And this means group velocity dispersion control. So we did that to control the position of this called dispersive wave or Cherenkov radiation waves that you can achieve in this frequency comms. Okay, that's all about comms. This is probably the most appealing application of this care-based nonlinearities in microcavities. But what I want to dive in today is this degenerate optical parametric oscillation process. I want to avoid that mess that we saw with the frequency comms. So just to recap, with Chi2 OPOs, you have a process where you pump the spontaneous parametric down conversion. You generate a signal in an Euler's field that is roughly at half of your pump frequency. And you can have the degenerate where the frequencies are identical. And if you look at the evolution equation for this field, the Stokes and the pump, or the signal in the pump field, what you see, there's a phase-dependent gain. Okay, so the pump to signal phase relation gives you this phase-sensitive amplification process that tells you that you might get oscillation in this resonator if the gain is maximum, which is offset always by pi. And what happens is indeed that, so below threshold, before you have enough pump photons to overcome your optical cavity losses, you have squeezing of your noise around the pump, around the signal and Euler frequencies. And if you go above threshold, you get this binary phase states being formed. So the binary phase states arrive because gain can only be offset by pi, so these two phases are well defined. There are two coherent states offset by pi, so you can get either 0 or pi phase pump to signal phase relation. People have been used this for various applications. Yesterday there was a talk by Hiro Takesui on how we can use this technique to build what they call coherent IC machines. And you can also use that for producing random numbers out of the interference of this binary phase states. Below threshold, of course, you can do all the quantum state processing. Squeezed states is a special case where it's very appealing to use Chi2 for it. Well, it turns out that doing this as an integrated platform is not that easy, because you are talking about working with a full octave of frequency span. And as I told you before, these structures are very dispersive. So it's not easy to engineer dispersion to phase match something that is a full octave apart. So that's why we are interested in Chi3 nonlinearity. So in Chi3, it's a cubic nonlinearity, so you have a sort of, your electron potential is symmetric, has inversion symmetry, and the result of that is that you can have wave mixing process that involves now 2 pump photons instead of 1. And by doing so, you can sort of have the same sort of energy spacing between the pumps and the signals and Eulers. So they are all lying within the same frequency band. Okay, so you can operate at telecom frequencies, and all the interactions will be constrained to that spectral region. Well, it turns out that if you work with two pumps and try to think of a process that energy is being converted to this intermediate mode here, you can get a very similar description that you get from Chi2. So you sort of mimic the Chi2 interaction. You can get a phase-sensitive amplification, where now the gain is determined by the product of the two pump waves. But again, signal is coupled to its quadrature. The two quadratures are coupled, and therefore you get phase sensitivity. Okay, so you can do that. This is sort of the picture. You have a pump mode, two pumps that you put into these waves here, and they will generate four-wave mixing processes, and eventually some of these four-wave mixing processes will populate the central mode, will give you an LPO. But along that, you get the sidebands, and you cannot get rid of them. So actually, this was demonstrated by Alex Gaeta group, and there was earlier theoretical work by Stefan Wabnitz in Italy showing that, what kind of dynamics you expect from this kind of system. But what they showed in this paper is that you can actually do two OPOs. These are two ring resonators here. And as I told, you can get the OPO process, but along that, you get the sideband. So this prevents you to keep increasing the OPO power, because as soon as you crank up the power, you start forming cascading, and eventually frequency comes out of this. So how to get rid of that? That's what we want to address. So again, this is what we had before. The idea here is to devise a device that can provide us three things. One, suppress non-degenerate four-wave mixing process. Second, give us GVD control on the fly. I don't want to fabricate the chip with 100 different devices and find one that works. I want to have on-site control of group velocity dispersion. And third, I want to get rid of the problem of pump phase noise, relative phase noise, because these two pump waves, they are not phase locked a priori. So they are drifting in frequency, phase diffusion, and therefore I pay a price of that in the OPO process. I want to devise a device that allows me to easily perform phase locking of the two pumps. So we learned a little bit earlier from coupled resonators from Professor Yang, so it's going to be easy on this side. So if you take two ring resonators and couple, or any two sorts of resonators and couple them together, the coupling rate in this case of ring resonators is given by the overlap of the optical fields in between the two waveguide structures that you have here, and the evanescent field leads to a coupling rate that can be represented in this matrix here, and once you diagonalize it, you find the supermodes of the structure. So you have a symmetric supermode and an anti-symmetric supermode. If you now, so I get two frequencies, right? I need three frequencies because I want to do a four-wave mixing process. So the way we do that is by adding a third resonator. If I add a third resonator to the game, now I have three supermodes as I diagonalize this matrix. And if I tune one of them relative to the others, I can see this avoided crossing diagram where right at the degeneracy point, I have three modes, central mode that stays where it is, anti-symmetric mode, slightly higher frequency, a bottom frequency for the symmetric mode. So you can see that if I tune this parameter, I get a regime where the frequency spaces is no longer even. It's even only if I'm sitting right at the degeneracy point. And if I go up or down, I can tune whether the bottom frequency gap is larger or the upper frequency gap is larger. So effectively, I'm tuning the local group velocity dispersion with this game. So this is possible to fabricate. So this is a simulation showing what kind of spatial profile you get for the supermodes. You have these three guys here, and the frequency splittings that you can achieve are on the order of tens of gigahertz for practical dimensions. I'm talking here about gaps, inter-ring gaps of a few hundred nanometers and ring radii of roughly 100 microns. So again, this will be used to address this pump phase locking scheme that I mentioned. So this is how it looks in the lab. So I have an input port, output port, I have my ring resonators, and to control the frequency of each of them, I add a heater that allows me to tune the resonant frequency of each mode. This is a picture of a microscope picture of the device. So these are the ring resonators. Here's the bus wave guide, and you have these heaters that deliver change the temperature of each resonator. And the measured spectra show that you get roughly 10 gigahertz frequency splitting, and the FSRs, the period at which these triplet repeats itself is roughly 240 gigahertz given by the ring dimension. So first thing we take care of, we want to ensure that overall, these rings have normal dispersion. So the distance between the triplet sets is reducing with frequency. So we measure that in the lab. All the 3 triplets indeed have a normal dispersion. The slope, the concavity of this parabola is pointing downwards. And this helps avoid the cascading of these pumps to generate the frequency combs. We did a 4-wave mixing experiment with that to show that, well, you can actually control the current in one of these microheaters and monitor the position of the spectral resonance. So these are the spectral resonance of the triplet, and show that for a given current, I can have larger frequency separation here than here, and for higher currents, smaller here than there. So this is effectively a region of anomalous dispersion, local anomalous dispersion, and this is a region of local normal dispersion. So indeed, we measure the efficiency of this stimulated 4-wave mixing process to show that, again, as you expect, when you reach close to zero dispersion, you get a maximum in conversion efficiency. Okay, so this addresses already 2 of the points I wanted to do, when suppression of non-degenerate 4-wave mixing, and now GVD control using microheaters. Okay, so we are on for the OPO demonstration. So what we did here is we pulse our pump to achieve slightly higher peak powers, but also we add this electro-optic modulator to generate my sideband. So I'm not pumping with 2 independent lasers. Instead, I'm pumping with one. I come with one carrier, generate 2 sidebands, and these sidebands will be used as pumps. So I have a phase locking between the carrier and the sideband. And this is all possible because I'm working at frequency spacings of tens of gigahertz, which are readily accessible with electro-optic modulators that you can buy on Tor Labs. So what we do in the lab is just really sweep this carrier towards this guy, and again, find a point where these 2 lasers, the 2 pumps, are resonant with the modes. And this is how it looks. We indeed see the 2 pumps. This density map here shows the OPO signal being generated from the 2 pumps, and this sort of concludes the demonstration of this. And we show also that by tuning the heaters, these are these 2 plots here, that by tuning the heaters, I can adjust the system to optimize the intensity of this OPO process that I have. Okay, I'm off of that part of my talk, which is good things. You can do local GVD control. That's something you cannot do with a standard single resonator approach. You can use RF pumps, RF generated tones, to drive the system, so you can ensure phase coherence between the 2 pumps. For example, squeezing applications, this is of uttermost importance. These particular devices that I've shown, they are fabricated in a foundry, Ligentech in Switzerland, so any one of you can order this sort of technology to your lab. There are a few things to work around. For example, filtering out the pumps, given that they're so close together, is a rather tricky challenge. It can be done, but it requires very fine filters. The 2 pumps might get into some instabilities that leads to a quite complex bifurcation analysis of the dynamical system that you're dealing with. And what we are looking in the future here is, one is looking at the time domain behavior of the system to generate, for instance, random numbers out of this, and also for squeezed state applications operating in the below threshold regime. Okay, so this is a bit on the standard care-based nonlinear optics, and now I'm going to show you something different that's also care in a way, as we learned from Markus Aspelmeyer earlier this week, but explores a completely different origin of the care nonlinearity, which is based on the mechanical interaction. So, in a nutshell, optomechanics can be described by this picture. So you have a resonator, you have an object. It can be the mirror itself, it can be an external object that is vibrating in the near field of your resonator. And when you have that, your frequency is oscillating back and forth because of a coupling between the mechanical degree of freedom and your optical frequency, right? This is the dispersive optomechanical coupling. In the frequency domain, you can think of this as generating Stokes and anti-Stokes sidebands, and what the resonator does for you is allows you to select the density of states that's favoring the pump when it's either in the red or the blue side of your system. so you can favor processes such as cooling of your mechanical mode or amplification of your mechanical mode. But there's something else that can happen in optomechanics, and this is what I want to dive in, is dissipation. So often you assume that these couplings are purely dispersive, that they only change optical frequency. Well, it turns out that's not quite true, and if you were to do the math of what happens, for example, this object here scatters light out of the resonator, so it also induces losses. So when you induce losses, what you see is that your loss term now depends also on displacement, and the effect of loss on a resonator is not to shift the frequency, but instead to shift the extinction of a resonator. And it does so because the interference is unbalanced, right? When you change the loss, the intrinsic loss of a resonator, you unbalance the interference that was responsible for giving this zero field transmission here. So this is sort of the readout effect that you get from this system. Okay, so this is a few work that were original work that inspired this whole field of looking into dissipative optomechanics. This is work from Hong Tang at Yale University back in 2009, and also a theory that was quite well developed by Christoph Bruder and Andreas Nunenkamp in Austria and Germany. So this is all figured out on the theoretical perspective on how you quantum mechanically understand the role of this dissipative dynamics, but there was very little experiments on this area. So we did a lot of work on this field. We're not going to dive into each of this work, but instead I chose to pick two examples that first motivated our steering to this direction, and second, a recent demonstration that explored this dissipative interaction. So this is a work that took a long time to conclude. It started back in 2011 when I was still a postdoc at Cornell University, working with Michal Lipson, and we set a collaboration with Paul McEwen, that's an expert in carbon nanotubes, and the question then was, can we measure the vibrations of a thermal Brownian motion of a single nanotube by approaching this nanotube to an optical resonator? So in a nutshell, this is like a 7 nanometer diameter object, dielectric object. It has a mass of about 1 femtogram, so very small, very large RMS Brownian motion, and we can pick it with a tweezer and approach it to the near field of a microresonator, silicon nitride resonator, and couple light in and out through the bus waveguide and read out what's going on with this, hopefully. So it turns out that this system is very sensitive to anything, including a Brownian motion of the nanotube. So first we just approach the nanotube towards the resonator. Here's a cross-section of your microresonator, and these are measured spectral transmission of your cavity. And when you approach the tube, what we see is that there's a clear reduction and extinction. And we further approach, you get further on. So very clear signal, right? There's no doubt the losses of this resonator were changed when this nanotube interaction occurred. But what is surprising is that most of the change is occurring in the loss, but not on the frequency. So this is a dominantly dissipative optomechanical interaction. So we use that to sort of understand Brownian motion dynamics of nanotube. I'm not going to get into the details, but essentially you can get a time trace in the optical domain in a photodetector that reveals all the mechanical modes that are present in the nanotube, and you can have sensitivities of 700 femtometers per square root hertz. So just to conclude on that, we use this to, because of this very high transduction gain, you have a very large bandwidth to monitor these vibrations. This allowed us to resolve what happens in a short time scale with the nanotube Brownian motion. So before this, what you would often see with electronical readout is a very broad mechanical peak that didn't allow you to probe what's going on the short scale dynamics. Okay, so this inspired us to look into dissipative optomechanics with this in this platform. But with the nanotube scheme, you cannot really engineer anything. You just hope that you're going to approach a tube and something's going to happen, and it turns out to be dissipative. You can maybe do metallic to dielectric engineering of your tube, but that's not that trivial. You need to work out the different rolling, the wrapping up of your tubes to get that. So we decided to think about a device that allows you to engineer this dissipative coupling. And this is work in collaboration with Simon Groblacher at Delft University. So here's a picture of the device. Let me go through with you. So we have an input waveguide. So you have this sort of optical and mechanical resonator. It has a defect in this crystal lattice that confines light. And it also has a mirror for phonons. So it reflects acoustic waves that try to propagate in this region. So you sort of confine acoustics and mechanics, acoustics and light to the same region. So these are the optical modes you get. So they're coupled because they're in the near field of each other. So you get a symmetric and an antisymmetric optical mode. And when you look at the mechanical side, because mechanics doesn't propagate in vacuum, right? Actually, they don't see each other. So the mechanical modes are isolated. You either have a mechanical mode that's on the top resonator or a mechanical mode that's in the bottom resonator. Okay? How you understand what's going on here? So what's the engineering of a loss here? So think about this system. No mechanics, just two resonators, right? One is coupled to the waveguide. The other one isn't. So you learn about these coupled modes. If I tune the frequency of one resonator relative to the other, I got this avoided crossing diagram, right? Typical that we saw earlier in the talk today, also from Professor Young. And it turns out that this losses is a combination. These losses are a combination of the internal losses and the external losses, the loss that takes energy out of the resonator into the waveguide. So you can clearly see an asymmetry here that one of the resonators is experiencing external loss that's not experienced necessarily by this outer resonator here, because it's not directly coupled to the waveguide. So what happens when you change this frequency? So again, you get this avoided crossing diagram, but we learned today as well from Professor Young, you get a hybridization, an anti-crossing for the real part of your frequencies. But the imaginary part, which translates to losses, they actually swap. So essentially what you get is one mode becomes the red becomes the blue and the blue becomes the red, and as they do so, they swap losses. So again, even without changing the loss, if I change the real part of the frequency, indirectly, I'm promoting a change in loss. So I found a way to, through a dispersive coupling, induce dissipation. Okay? So it's an indirect dissipation mechanism. So what happens if you couple to the mechanics? Well, the mechanics is going to do is to make this frequency oscillate in time, as I shown before. So now the mechanics is modulating the loss of your resonator through this avoided crossing interaction. So essentially, dispersive induced dissipative. Okay, so this is how we test in the lab. Essentially what you have, don't worry about this complicated setup here, but there's a laser, there's your resonator, the reflected light is collected and shined in two devices. A photodetector that tells us the optical transmission. Here's a measured transmission for this device. Very large frequency splitting. This means that the optical modes are very strongly coupled. And on the other side, we've shined light coming out into our radio frequency photodetector and make a spectral analysis of this device. How it looks like? Well, let me go through with this. So what I'm showing here is, on one axis, I'm going to vary the laser detuning relative to the resonator. So there's a pump. I scan the pump across the resonance. I'm showing here the optical transmission as measured by this low photodetector. And here, I show the power spectral density as measured by the radio frequency spectral analyzer, right? And each scan on this line corresponds to a different power spectral density. So let's animate this to see what happens here. So as you scan your laser, you see these different regimes. And essentially, what's going on here is that I'm operating in the so-called sideband resolved regime. So my mechanical frequencies are larger than the optical line width. So that's why you only see the transduction of your signal when you're roughly detuned by more or less the mechanical frequencies, which is about 5 gigahertz. But what is striking in this plot is this symmetry of this figure. So let's explore that. So if you look at a horizontal cut at a given detuning, you see two peaks. The origin of these two peaks are the two mechanical modes that I mentioned earlier, from one resonator and from the other resonator. Remember that the optics see both resonators. Optics is spread out. So I probe the two modes with a single optical degree of freedom. But what's striking is when you cut in a vertical line here. So you see this asymmetry that the blue sideband or the red sideband is one is stronger than the other, but this asymmetry is flipped when I go to the other resonator, which is shown here. So what explains that? So often in this field, there's something called dynamical back action. We know that if you put your pump in the blue sideband, the blue detuned relative to the resonator, you increase the phonon count. If you put in the red sideband, you reduce the phonon count. Well, this is not what's causing this. Because you can see that if I flip the optics, the optical mode, they have the same optical quality factor. I reverse this role. So what's going on here? I'll just put a picture that fully explains what's going on, and it's based on the interference between dissipative dynamics and dispersive dynamics. So follow with me. So if your laser is sitting at 0 detuning relative to the resonator, what you're going to see is that dissipative coupling changes distinction and leads to a signal. Dispersive dynamics, though, in the first order, doesn't change anything. However, if you now put your laser either red detuned relative to your resonator or blue detuned, the interference between these two effects on one side leads to a weaker signal, and on the other side leads to a stronger signal. So this is what's going on. So you can now think of a device that you explore everything that you do with optomechanics, but you can control the strength of that just by choosing which side of the interaction you are using. So this is what you would expect from dispersive theory, the dashed lines, and the blue lines shows what you get from the combined situation. And what I'm showing here is the line width of your mechanical resonator. So effectively what I'm showing is you can increase the line width, therefore cool down your mechanical mode, remove phonons from the system, or you can pump the system, pump phonons into the system. And this shows that this scheme allows you to control the strength of that. And more importantly, this is happening with only 1% of dissipative relative to dispersive coupling. As a perspective, we made the calculations, what would happen if you were to increase this by a few percent, go to 3, 4, 5%. And this is what shows that at about 5%, for example, you can actually completely cancel cooling or amplification by destructive interference between these two effects. Okay, so overall remarks, I think photonic molecules on the care side can really shape the care interaction, but also can shape optomechanical interactions as we've shown here. For example, intermediating dispersive to dissipative coupling. This was the first time that this regime of dissipative coupling appeared in the resolved sideband limit, where you can really select which Stokes or anti-Stokes process you want to excite. There's a lot of recent work on looking into this when you couple many mechanical degrees of freedom and looking what they call this dissipative multimode dynamics that's extremely rich and interesting. And I want to close up with this highlight. So there are many works in this area in our group. I'm not going to go into the details, but if you want to check our website or our references, you're invited to see what else we are coming out. And just to conclude, what is the connection between these two areas? Why you're talking about mechanics and Kerr? So as soon as we are able to do Kerr nonlinearities in a frequency range that is in the gigahertz regime, we can start thinking about interacting Kerr effect with optomechanics that often were set really apart because FSR of resonators were in the hundreds of gigahertz and the mechanics is operating at the megahertz or the gigahertz level. So we are stretching the mechanical frequency a bit up and pulling down the optical frequencies a bit down. So eventually you can think about what, for example, intracavity squeezing through Kerr effect, how does that interact with the mechanics for sensor applications, for example. Okay, I'd like to conclude thanking all the people involved in this work, both in the Kerr applications that I described and also on the optomechanics, especially Professor Thiago Alegre, which is my longtime partner in most of the experiments I've shown here, and also the whole team at University of Campinas that were involved in supporting this work. And of course, the people who pay the bills. Thank you very much.
Thank you, Gustavo, for the great talk. Questions? Well, I'll start with one. So, in the beginning of your presentation, you talked about the drawbacks of silicon. And I guess you have to make it do with it because all the industry relies on it. But if it didn't, if you could pick something that's the standard, what would you pick rather than silicon?
So it's not quite true that the industry doesn't develop anything else. For example, 3.5s are very well developed, not as cheap as silicon, but very well developed. So you can do fabrication with 3.5s. 3.5s have light emission, they have many advantages. So I see nowadays a convergence. A lot of people are actually plugging 3.5s into silicon to actually overcome these limitations of silicon itself. But 3.5s also suffer a lot from nonlinear absorption. So if you want to do nonlinear optics with 3.5s, you better get ready to handle that. And it's not easy. Lithium niobate, though, it's something sort of an old material that people use everyday nonlinear optics lab, but now has been ported, let's say, into this thin film lithium niobate platform and has been enabling a lot of Chi2 physics to happen in these integrated platforms. But what is underlying is a silicon chip. So in the end, everything relies on silicon to build upon. Like 2D materials is an exploding field, like people putting 2D materials on top of the silicon structures, or silicon nitride, or lithium niobate, to actually bridge these advantages that 2D material, like single photon emitters, for example, in tungsten diselenide, just one example. So there is like, I wouldn't pick one, but now I think clearly the conversion of all these technologies into a silicon-based platform is what is being used across the world to derive this most novel results in the science side.
More questions? Vlad?
Thank you for a wonderful presentation. So my question is that in regular nonlinear optics, thermo-optical effects are considered to be the strongest nonlinear effects. So I was wondering, so do those effects play a role in your system, and if so, well, how do you handle those?
You said Chi2 nonlinear effect?
No, thermo-optical. So,
Thermo-optical.
Yeah.
That's an excellent question. Thermo-optical is the strongest effect you're gonna ever see in this platform, because of course heat, there's nowhere to go. You have a silicon dioxide underneath, which is very low thermal conductivity, so heat stays there. That brings two things. One, you burn devices. So often you look at the damage that you can get in these waveguides, and you are unlikely to be able to put more than 1 watt of CW power in them, and they essentially melt when you do so. The nonlinear side, you get bistability. For example, I didn't discuss, but this plot, you can see on the left here, so you see this tilted triangle resonance shape, that is due to thermo-optic effect. So again, it's better or worse in different, like silicon is maybe a little bit better than silicon nitride, depending on the amount of heat that it generates, but it is a major, depending on what you're doing, like you cannot park your laser on that side of the resonance. So if you want to do cooling, for example, the cooling side is the red detuned side, and you cannot get a stable detuning on that side. So it's really a drawback, and people try to work around it, but in the end, it's a cat and mouse game. So.
More questions?
People have demonstrated tens of meters. So it's really about how big of the chip you want, right? So the picture I shown from Tobias Kippenberg group, this is like a 10 by 10 millimeter chip, 1 centimeter squared, right? And people do larger chips. And if you can accommodate larger chips, you can go to even tens of meters. For the slow loss, silicon, no, because of the loss, but silicon nitride, you can do it, tens of meters.
I don't see any more questions, so let's thank Gustavo again.
Well, this is the end of the plenary section, but it's not the end of the conference. We still have seminars in the afternoon. But I don't think we're going to get together again. So I want to thank you all for coming to the conference. I hope you had a good time. We apologize for the inconveniences that happens during the organization, but well, that happens everywhere anyway. And I want to thank you all, the group that helps, the secretaries, the people in the laboratories that we have, Lucas, Amilson, Marcos, Daniel, which is not here, Didi, Miriam. So who is from the group? Christina, Johan. So everybody helps to make the things to happen. So thank you very much. I hope that at the end of the day you can still have energy to take your route to your house, whatever it is, and hope when we organize some next meeting you come back to São Carlos. Thank you very much. Somebody forgot an umbrella and a coupling for the computer. We're going to hang to it then. Thank you very much.